A quiet region framed by mountains can give the impression of stability, of landscapes that have settled into permanence over thousands of years. Yet beneath northern Utah, movement continues at a pace too slow to notice in a lifetime, but powerful enough to reshape entire cities in a matter of seconds. The question is not whether the ground will move again, but how prepared the region is when it does. How does a fault system capable of producing some of the strongest earthquakes in the interior of the United States remain so often overlooked? Why do millions live directly along its path? And what does the geologic record reveal about the forces building quietly beneath the surface? When earthquakes in the United States are considered, attention is often drawn to California, or perhaps to Alaska, the most seismically active state in the country. Some may also think of the Cascadia subduction zone in the Pacific Northwest. Far less attention, however, is given to Utah, despite the presence of a major fault system running directly beneath Salt Lake City and surrounding communities. This system, known as the Wasatch Fault, poses a direct threat to more than 2.8 million people living along the Wasatch Front. The Wasatch Fault is responsible not only for uplifting the Wasatch Range, but also for generating powerful earthquakes in the region. Scientific assessments indicate a 57% probability of a magnitude 6.0 or greater earthquake occurring within the next 50 years, alongside a 43% chance of a magnitude 6.8 or stronger event. In extreme scenarios, the fault is capable of producing earthquakes as large as magnitude 7.5, an event that would have catastrophic consequences for northern Utah. Stretching roughly 220 miles, or about 354 kilometers, from Fayette to Malad City, the Wasatch Fault marks the eastern boundary of the Basin and Range Province, a vast region characterized by crustal extension. This province extends westward to the Sierra Nevada. The Wasatch Fault is classified as a normal fault, meaning that the block of rock beneath the fault rises while the block above it drops. This motion is driven by extensional forces that pull the Earth's crust apart. The mechanics behind this process are rooted deep within the lithosphere. As tectonic stress accumulates over centuries, the crust stretches, thins, and fractures. In the Basin and Range Province, this stretching is not a singular event, but an ongoing process that has persisted for millions of years. The result is a landscape defined by alternating mountain ranges and valleys, known as horsts and grabens. These features are not static formations, but expressions of continuous deformation, where blocks of crust tilt, rise, and sink in response to shifting forces below. As the crust stretches, magma from the mantle rises upward, fracturing the surface and contributing to the formation of these structures. The Wasatch Fault sits along the eastern edge of this system, where the extensional forces of the Basin and Range Province meet comparatively stable crust to the east. This boundary creates a zone of concentrated stress, making the fault particularly active compared to others in the region. Geologic records provide a long-term perspective on this activity. Over the past 6,500 years, the Wasatch Fault has produced at least 26 surface-rupturing earthquakes of magnitude 6.5 or greater. These events are identified through trenching studies, where layers of sediment reveal past ruptures, offsets, and periods of quiescence. Each rupture leaves a distinct signature in the landscape, from displaced soil layers to fault scarps that can still be observed today. The most recent of these large events occurred approximately 500 years ago near Nephi. Based on available data, major earthquakes along segments of the Wasatch Fault tend to occur every 300 to 400 years on average. The elapsed time since the last event suggests an elevated level of concern, although such averages do not function as precise predictors. Earthquake recurrence is inherently irregular, influenced by variations in stress accumulation, fault geometry, and interactions between adjacent segments. The Wasatch Fault is not a single continuous break, but a system divided into 10 distinct segments, each with its own behavior and recurrence interval. Some segments have produced earthquakes more recently, while others have remained quiet for far longer than expected. The segment near Brigham City, for instance, has not experienced a major rupture in over 2,500 years, despite having a shorter average recurrence period. This inconsistency underscores the difficulty of forecasting seismic events, as the absence of recent activity does not equate to reduced risk. Urban development along the Wasatch Front has expanded significantly over the past century, placing a growing population directly within the zone of potential impact. Cities including Salt Lake City, Ogden, and Provo lie within close proximity to the fault, often on sediments that can amplify shaking. These sediments, deposited over thousands of years by ancient lakes and rivers, form a basin that can trap seismic waves, increasing their intensity and duration. A more recent reminder of this hazard occurred on March 18, 2020, when a magnitude 5.7 earthquake struck near Magna, just west of Salt Lake City. The earthquake originated at a depth of about 10.6 kilometers, or roughly 6.6 miles, and was widely felt across the region. Although no fatalities were reported, the event caused injuries, triggered more than 2,800 aftershocks, and resulted in approximately $629 million in damages. Notable structures such as the Salt Lake Temple sustained damage, including the loss of the Angel Moroni statue's trumpet. Other buildings, including the Rio Grande Depot and St. Mark's Episcopal Cathedral, were also affected. The event exposed vulnerabilities in both historic and modern infrastructure, highlighting the challenges of maintaining resilience in a seismically active region. Despite its impact, the 2020 earthquake was considered moderate. A much larger event, often referred to as the anticipated major rupture, could be significantly more destructive. Because earthquake magnitude is measured on a logarithmic scale, a magnitude 7.2 earthquake would release roughly 178 times more energy than a magnitude 5.7 event. This exponential increase in energy translates directly into stronger ground motion, broader areas of impact, and more severe structural damage. Projections by the United States Geological Survey indicate that a magnitude 7.0 earthquake near Salt Lake City could result in 2,000 to 2,500 fatalities, thousands of serious injuries, and the displacement of more than 84,000 households. Infrastructure systems, including water, electricity, gas, and sewage, could be disrupted for months. Transportation networks could be severed by ground rupture, landslides, and damaged bridges, complicating response and recovery efforts. One of the most significant hazards associated with such an event is liquefaction, a process in which water-saturated soils lose strength during shaking and begin to behave more like a liquid than a solid. This phenomenon is particularly concerning in the Salt Lake Valley, where loose, waterlogged sediments are widespread. Buildings constructed on these soils may tilt, sink, or collapse, even if they are structurally sound, as the ground beneath them loses its ability to provide support. The geological conditions that contribute to liquefaction are a direct result of the region's history. Much of the valley was once covered by ancient Lake Bonneville, a massive inland lake that existed during the last ice age. As the lake receded, it left behind thick layers of fine-grained sediment, including silt and clay, interspersed with sand deposits. These materials retain water and are highly susceptible to liquefaction during strong shaking. Even larger earthquakes, such as a magnitude 7.5 event, could have far more severe consequences, potentially resulting in tens of thousands of casualties and widespread displacement. However, modern building codes in Utah help mitigate these risks. Seismic design standards, widely implemented since 1970, ensure that many structures are built to withstand strong shaking without collapsing. These standards focus on life safety, allowing buildings to sustain damage while reducing the likelihood of catastrophic failure. Older unreinforced masonry buildings remain among the most vulnerable structures. Many of these buildings were constructed before modern seismic codes were established and lack the reinforcement needed to resist lateral forces. Retrofitting efforts have strengthened some of these structures, but a significant number still pose a risk, particularly in historic districts. A comparison with the 2010 Haiti earthquake illustrates the importance of such building standards. That earthquake struck near Port-au-Prince and resulted in over 160,000 deaths, largely due to inadequate construction practices. While a similar magnitude event in Utah would still be devastating, the presence of seismic codes would likely reduce the overall loss of life. Preparedness remains essential for residents living along the Wasatch Front. The geological forces shaping the region are ongoing, driven by processes that operate on timescales far beyond human perception. The Wasatch Fault continues to accumulate strain, storing energy that will eventually be released in the form of another earthquake. The timing of that release remains uncertain, but the conditions that make it possible are well understood and persist beneath the surface. Beneath the visible landscape of cities, roads, and infrastructure, the boundary between stability and sudden movement is defined by fractures in the Earth's crust that extend deep into the subsurface. These fractures are not isolated features but components of a broader tectonic system that spans much of the western United States. The Basin and Range province within which the Wasatch Fault resides represents one of the most extensive zones of crustal extension on the continent. This extension is driven by a combination of forces, including the gravitational collapse of thickened crust and the influence of deeper mantle dynamics. As the crust is pulled apart, it creates space that must be accommodated, leading to faulting and vertical displacement. Over time, these processes produce the characteristic pattern of parallel mountain ranges and valleys that define the region. The Wasatch Range itself is a direct product of this activity. Rising sharply from the valley floor, the mountains owe their elevation to repeated movement along the fault, where one side is lifted relative to the other. This uplift continues incrementally with each seismic event, contributing to the long-term evolution of the landscape. At the same time, erosion works to counterbalance this uplift, wearing down the mountains and transporting sediment into the valleys. This interplay between tectonic forces and surface processes creates a dynamic equilibrium where the shape of the land is constantly being reshaped by competing influences. The presence of multiple fault segments adds another layer of complexity. Stress can transfer between segments, potentially triggering earthquakes in adjacent areas. This interaction means that a rupture on one part of the fault system could influence the timing and location of future events elsewhere along the Wasatch Fault. Understanding these interactions remains an ongoing challenge, as the subsurface geometry of the fault is not fully visible and must be inferred from indirect observations. Seismic monitoring networks provide real-time data on smaller earthquakes, which occur frequently, and help researchers map active structures beneath the surface. These smaller events, while often unnoticed by the public, offer valuable insights into how stress is distributed and released over time. Patterns of seismicity can reveal areas where strain is accumulating, as well as regions where it may have been recently released. Geodetic measurements, including satellite-based observations, also contribute to this understanding by tracking subtle movements of the Earth's surface. These measurements can detect shifts on the order of millimeters per year, providing evidence of ongoing deformation. Over decades, these small movements accumulate, reflecting the gradual buildup of strain along the fault. The combination of geological, seismic, and geodetic data forms the basis for current hazard assessments. These assessments do not predict specific earthquakes, but instead estimate probabilities over longer periods. They provide a framework for planning, allowing communities to evaluate risk and implement measures to reduce potential impacts. Yet even with this knowledge, uncertainty remains a defining characteristic of earthquake science. The exact conditions that lead to a rupture are influenced by factors that are not fully understood, including variations in rock properties, fluid pressures, and the history of past events. This uncertainty complicates efforts to anticipate when and where the next major earthquake will occur. The pattern of life along the Wasatch Front continues with little visible interruption, shaped by routines that rarely account for the forces accumulating beneath the surface. Roads expand, residential areas push outward, and commercial centers grow denser, all within a corridor that follows the base of the Wasatch Range. This concentration is not accidental. The same geological processes that created the fault also formed a landscape favorable for settlement, with access to water, relatively flat terrain, and proximity to natural resources. Yet these advantages are inseparable from the underlying risk. Across Utah, much of the population remains situated within a narrow band that parallels the Wasatch Fault. This alignment means that a large portion of the state's infrastructure is exposed simultaneously to the same seismic source. Highways, rail lines, pipelines, and transmission systems often cross or run adjacent to fault segments, creating multiple points of vulnerability. In a major earthquake, disruptions would not occur in isolation, but would cascade across interconnected systems. The Wasatch Front, extending from Brigham City through Salt Lake City and southward toward Provo, represents the economic and population center of the state. Within this region, ground conditions vary significantly, influencing how seismic waves behave as they travel through different materials. Bedrock areas tend to experience less amplification, while basins filled with sediment can intensify shaking. These differences can result in uneven damage patterns, where some neighborhoods experience severe impacts, while others nearby are less affected. One of the defining characteristics of large earthquakes is not only the intensity of shaking, but its duration. In a magnitude 7.0 or greater event, strong shaking can persist for several tens of seconds, long enough to weaken structures that might otherwise withstand shorter bursts of motion. The cumulative effect of sustained movement increases the likelihood of structural failure, particularly in buildings that lack reinforcement or were constructed under older standards. Surface rupture presents another direct hazard. In areas where the fault reaches the surface, the ground can shift horizontally and vertically by several feet or more than 1 meter in a matter of seconds. Any structure built directly across the fault trace is at risk of being torn apart by this displacement. Although zoning regulations have sought to limit construction in these zones, development pressures and incomplete mapping have left some exposure in place. Beyond the immediate effects of shaking and rupture, secondary hazards would play a significant role in shaping the overall impact. Landslides are a major concern along the steep slopes of the Wasatch Range. During intense shaking, unstable rock and soil can break loose, traveling downslope and threatening communities at the base of the mountains. These landslides can block roads, damage structures, and in some cases alter drainage patterns, increasing the risk of flooding. Fire represents another critical risk, particularly in urban areas where gas lines, electrical systems, and damaged structures can combine to create ignition sources. If water systems are compromised, firefighting capabilities may be limited at the very moment they are needed most. Historical earthquakes in other regions have demonstrated that post-earthquake fires can rival or even exceed the damage caused by shaking itself. Water infrastructure is especially vulnerable in the Salt Lake Valley. Pipelines that cross fault zones or rest within liquefaction-prone soils are susceptible to breaking. Loss of water supply would affect not only residential needs, but also emergency response efforts. Similarly, wastewater systems could be disrupted, creating sanitation challenges that extend beyond the immediate aftermath of the event. Electric power systems, which rely on a network of substations and transmission lines, could experience widespread outages. Even if some components remain intact, damage to key nodes can interrupt the flow of electricity across large areas. Restoration efforts would be complicated by access issues, as damaged roads and debris could delay repair crews. Transportation networks form the backbone of regional connectivity, and their disruption would have immediate consequences. Bridges, overpasses, and interchanges are particularly vulnerable to seismic forces. Damage to these structures could isolate communities, hinder evacuation efforts, and delay the delivery of essential supplies. Airports and rail systems, while designed with some level of resilience, are not immune to the effects of strong ground motion. In the broader context of the United States, the Wasatch Fault represents a unique convergence of geological activity and population density outside of the more widely recognized seismic zones. Unlike coastal regions where tectonic boundaries are more apparent, the Basin and Range Province reflects a different type of deformation, one that spreads across a wide area and manifests through numerous faults, rather than a single dominant boundary. The United States Geological Survey has developed scenario models to better understand the potential consequences of a major earthquake along the Wasatch Fault. These models incorporate data on population distribution, building types, infrastructure, and ground conditions to estimate outcomes under different scenarios. While the specific numbers vary depending on the assumptions used, the overall picture remains consistent. A large earthquake would result in widespread disruption that could take months or longer to fully address. And if you found this video informative and valuable, consider supporting the channel by liking, sharing, and subscribing. Tap that hype icon to help this video reach a wider audience so more people can stay informed and prepared.